In the electric field defined by 2z, y plus 1, and x plus 1, we'll be finding the position and velocity of a 0.1 kilogram particle with a charge of 1 coulomb that is initially at rest at the origin at times 5 seconds, 10 seconds, and 15 seconds. So we're going to start with, we just know that it's at the origin, at rest initially, so we can calculate our initial force on the particle using our force is equal to our charge times our electric field. And so we just plug the point 0, 0, 0 into this equation for our electric field, and that spits us out a force of 0, 1, 1. And so we're going to use a kinematic equation to calculate the position after 5 seconds. And so we've substituted force over mass in for our acceleration to give us a vector that we can actually use. And so we simplify that down, and we get this for our position after 5 seconds. And then we're going to use this relationship to find our velocity after 5 seconds. So we're going to plug in for our net force, which is the force that we found earlier. We're going to plug in 5 seconds because that's how much time has elapsed since the original, since the beginning of the experiment. Our mass is still 0.1 kilograms. We're trying to find our velocity at 5 seconds, and we're going to plug in 0 for our velocity at 0 seconds since our particle is at rest. So we plug those in, and we solve for velocity at 5 seconds, and we get out 0, 50, 50. So now we're going to move on to calculating position and velocity at 10 seconds, but we need to start with our force at 5 seconds. So we do the same thing we did before, but instead of plugging in the origin to our electric field equation, we've plugged in the point that we found over here to give us this vector. And so again, we plug this into a kinematic equation very similar to what we did before. Only this time, because we have an initial velocity, we've added a velocity dependent term. And so again, we go through the same process of simplification and adding all of our vectors up. And then we get this for our position at 10 seconds. And so we're going to do the same process again, just using the same momentum relationship and plugging everything in and solving out for our velocity at 10 seconds. It's worth noting that delta t is still 5 seconds since we're going from 5 seconds to 10 seconds. But everything else is fairly straightforward and just simplification. And this is our final velocity that we end up with for 10 seconds. And then we're going to do this one more time for 15 seconds, but yet again, we have to start with our force at 10 seconds. And so we plug in our position at 10 seconds that we found previously into the equation for our electric field, and that will spit us out our force vector at 10 seconds. And so again, we plug it into our kinematic equation, and because our numbers are getting large, our vectors are getting kind of lengthy. So I'm going to do the best I can to keep everything in frame here. And so again, we plug it into the kinematic equation, and time is still 5 seconds because that's the number of seconds in between 10 seconds and 15 seconds. And so we just simplify it down after plugging it into the kinematic equation, and this is our position vector that we get out. And so then we're going to go into calculating the velocity at 15 seconds. And so we do the same thing. We use the same momentum relationship we did the previous 2 times. We just have slightly larger numbers, and it's the same process. You just plug in for everything and then solve for our velocity at 15 seconds, do some simplification, and it spits us out our final velocity at 15 seconds.